For the screencast for chapter number 12, I have chosen a problem which says that the circuit consists of two flashlight batteries, as you can see, and a thick filament bulb and a thin filament bulb. This is the thick filament and this is the thin filament bulb, and very low resistance copper wire. And the number A says calculate the number of electrons that flow out of the battery every second at location A. This is the position. So we are given the resistance of thick filament equals 40 ohms, you can see, and for the thin filament is 10 ohm. As you know that the loop rule says that you can't gain energy in a round trip, which is basically the energy principle but on a per coulomb basis. So the total volt in the round trip equals 0, which can be given by 2 EMF for the two batteries, IR10 for the thin filament, I the current flowing into resistance for thick filament equals 0. So now solving for I, which equals 2 EMF divided by bracket R10 plus R40, and substituting them by the value given, it comes out to be 6 into 10 to the power minus 2 ampere. And we know that delta Q, we know that the I equals the electron flowing per second equals current divided by charge, and as we got current to be 6 into 10 to the power minus 2 ampere, and the charge for the electron is 1.6 into 10 to the power minus 19 coulomb. The electron flowing per second through the location A comes out to be 3.8 into 10 to the power 17 electron per second. For the question number 2, the problem says draw an accurate graph of potential around the circuit with x-axis running from A to H, level y-axis with numerical value of potential. So x-axis is the location and y-axis is the volts. You can see the volt for A to B is same, is 0, and when moved from B to C location there is a rise in the volt, and from location C to D it remains same, and when it moves from D to E there is a huge bigger electric volt, and for E to F it is constant, and when it moves to A it always drops down. This is due to the fact that a bigger field is needed in thin filament bulb, so the surface area gradient across the thin filament bulb is much higher than the surface charge gradient across the thin filament, and the surface charge gradient across the copper wire is extremely small because only a very electric field is needed in these wires. So the this gradient is so small to show up on this diagram, so I have shown the surface charge approximately uniform on the wire. And for number C, it says the tungsten filament in the thin filament bulb is 8 mm long and has a cross-sectional area of 2 into 10 to the power minus 10 meter square. How big is the electric field inside this metal filament? The electric field in the filament of thin filament bulb can be found from the potential difference, which we can get from E equals delta V by L, where delta V is the drop in potential, which can be given by IR. Now putting I and R40 for the for this filament bulb and substituting them by the value given, it comes out to be 300 volt per meter. And we need to be really careful with the units over here. And for the current is ohm, ampere, and for resistance is ohm, and for L is meter. And we know that ohm IR can be given by volt. And for the number D, it asks us what is the power output of the battery. We know that power is given by electric potential energy change over time, and we know the electric potential energy change can be given by delta Q dot delta V, and we know that delta Q per delta T is the amount of charge moved per unit, which is current, and substituting delta Q or delta T by I, we have a formula power equals to I delta V, and now putting the value and substituting them by value, it comes out to be 0.118 watt. Thank you.